Welcome again to this course Thermodynamics. I am Assistant Professor Joy Arlis O. Vergara, and I will be with you for the next few topics in this course. Before going into discussing new concepts, let us first review some of the important lessons you've learned in the previous unit. You learn about temperature and heat, where you discuss concepts such as thermal expansion, where for any object given with some change in its temperature, this object may change in its length, its area, or its volume. You also know about how to measure, how to quantify the change of heat given or absorbed by a certain system of objects or particles. You also know about some concepts in how to determine the amount of heat experimentally. You also know about the mechanisms of heat transfer or the transfer of energy in a form of heat. You know about convection, you know about conduction, and you know about radiation. Again, I am Professor J. Arls Vergara, and with me in this course is Dr. Jonathan P. Manigo. And for this topic, we'll be discussing about equations of state. We are not talking about the state such as places, but we will be discussing about the state of an object or collection of objects or an ensemble of particles. Equation of state relates to the thermodynamic state variables. We'll define these variables later. And this equation is used to predict, to calculate the state of a system or a group of particles inside a considered volume when one state variable will be subjected to change. These state variables are quantities that describe the thermodynamic state of a certain material or a system of particles or simply a system. And these are the most common state variables. We have the pressure, the volume, and the temperature. Let us consider, for example, if you are to heat a certain volume of water on your electric stove, if you are getting a water which is exposed in your room, then initially you can assume that the temperature of the water is just equal to the room temperature. Once you subject the transfer of energy, for example, for this case, we have a conduction and convection. The amount of energy from this heat from the electric stove will be transferred to the water, which is initially at room temperature. And visually and based on our experience, I assume you also had this experience that when you add a certain amount of heat to that water, at a certain later time, there will be changes. There will be observable changes in the behavior and the state of the water. Some will evaporate, and eventually the volume of the water will reduce. This happens with a very obvious change in temperature. For us to have a basic understanding on how these gas particles, how these particles behaves, we'll consider an idealized model. We have this ideal gas. This is not a real gas. This is a theoretical one, which are treated as point particles, where each particle in an assembly or as an sum or a system of ideal gas particles, each one of these particles do not carry with them a certain volume. So they are just point particles in space or in a certain volume. To simplify it further, each particles do not interact with each other. They are just moving in space without considering the behavior or what is happening or what other particles are doing within that volume. Say we have the ideal gas here inside this rectangular volume. Ideal gas particles moves around in that volume without considering the presence of other particles. And as they move, what they are doing is just moving around, hitting the surface of that boundary without necessarily interacting with other objects. However, for non-ideal gas, the situation is now different because, again, these particles can move freely inside the volume, but these particles has the tendency of bumping with one another, and of course its motion is also being affected by the presence of other particles. We will discuss about that more later. So for ideal gas, we have this ideal gas law. This is an equation of state for the ideal gas. And this is a very simple equation. We have the PV is equal to nRT is also equal to nKT with the following definitions. N is simply the number of moles, where this is just the ratio between the mass of the substance and the 1 mole of this substance. And we have the gas constant R given this value. And of course, T is our temperature. And we have this N, which represents the number of particles, where it can be calculated using Avogadro's number with this value. And we have the Kb, which is the Boltzmann constant, with this experimentally known value of 1.38 times 10 to the power of minus 23 joule per Kelvin. Now, for the ideal gas equation we introduced, we will consider a certain gas inside a container of fixed dimension, a rigid container. Now, there is a situation here which relates to our previous knowledge about the interaction of two objects. Once we introduce gas into the volume of that container, of course, again, these are individual particles which are free to move inside the container. So what will happen is, these gas particles, as they move inside the container, they will hit the surface, the inner surface of that container or the walls of that container, giving a certain amount of force against the wall. And by Newton's third law, we know that there should be a reaction to that force introduced by the particles. And that is why we have another force which is introduced by the walls or the inner walls of the container against the particles which are hitting the walls. So we have this force per unit area exerted by the container on the gas inside, and of course we have the force per unit area exerted by these gases on the walls of the container. So if we will consider that amount of gas we introduce into the container, we have the fixed amount of gas. So we have the fixed value of mass. We have the fixed number of moles of that gas. Then what will happen? If we are to introduce from this equation, if we are to introduce a fixed amount of gas, fixed value of gas, then these terms should be equal. Under different values of temperature, this ratio should remain constant. Meaning, at any given time, from the moment we introduce this gas inside the container, this amount of gas will remain the same. And if we are to change one of these parameters, one of these state variables, there should be a change on the other state variable, thereby giving us a more simpler form of the ideal gas law, by which the ratio PV over T is always constant. That means at its initial condition, say P1 V1 over T1 should always be equal to P2 V2 over T2. That is constant. And that's for ideal gas. You might ask, how about non-ideal gas? Here we have van der Waals equation. According to this formulation, this is a more realistic approach in dealing or discussing about the behavior of gases. The difference between the two is that, again, as mentioned, ideal gases are treated as infinitely small, okay? Thereby, they are not themselves occupying volume within that space. However, for a more realistic situation, gas particles do carry with them their own volume. These gas molecules has volume. And the more you put these realistic gas molecules inside a volume, this will reduce the amount of space or volume where these gases can move around. And other than that, if you can remember in your general physics concepts or in your high school physics, there is this gravitational force concept where if you have objects, each carries with them their respective masses, there should be a force of interaction between these particles or objects. And that is the same concept that is happening into a real gas model, where other than exerting forces on the walls of its containing volume, these particles also are exerting forces, attractive forces with one another, thereby resulting to a lesser total or net force exerted on the walls of the boundary or the bounding container. And this is our equation. We have P an square over V square times the difference between the volume and the NB is equal to nRT, where the parameters A and B are constants which are dependent on a type or kind of gas which will be considered in a particular mathematical calculation. So let us consider a few examples. First, consider a volume of gas at STP. The condition STP, or the standard pressure and temperature, is a situation where the gas is defined to be at a temperature of 0 degrees Celsius, or for our standard or our SI unit, that is 273.15 Kelvin. And at STP, the pressure is considered to be 1 atm, or that is 1.013 times 10 to the power of 5 pascals. If you want to keep a mole of an ideal gas at STP, how big a container do you need? Remember the ideal gas law equation, where we have PV is equal to nRT, and since we will be solving for the volume of the container for this 1 mole of ideal gas, then we will be using this equation. V is just equal to nRT over P, where we are given with a mole. So we have 1 mole of gas, and we have the constant R, and at standard temperature, which is equal to 273.15 Kelvin, divided by the pressure given, then we simply solve for its numerical value. We have 0.224 cubic meter, or simply that is 22.4 liters. Again, if you are to contain a 1 mole of ideal gas at STP, you need a container with a volume of 22.4 liters. Just to give you an idea how big is this volume of container, then we have these standard buckets available in the market. So the biggest available bucket in the market, that is roughly 20 liters. So at least if you can contain a 1 mole of ideal gas at STP, you need this amount of volume available. For our second example, we have to compress gas mixture inside the engine of a car. So this is a gasoline engine. In an automobile engine, a mixture of air and gasoline is compressed inside the cylinder of the engine, and it is then ignited by a certain component called spark plug. A typical engine has a compression ratio of 9:1. That means that the gas in the cylinder is compressed to 1/9 of its original volume prior to ignition. That is the required compression ratio for your engine to be able to burn the fuel inside the cylinder. The initial pressure is at 1 atm, assuming this is at sea level, because atmospheric pressure at sea level is 1 atm. And the initial temperature is 27 degrees Celsius. And that's during rainy season where we have this temperature of around 27 degrees Celsius. If the pressure after the compression is 21.7 atm, find the temperature of the compressed gas. So this is our engine, where inside the engine we have these cylinders. This is called the piston. This is our combustion chamber, where the gases, the fuel and the gas are mixed, and as the piston moves up, this will compress the mixture inside the combustion chamber. Our task now is to solve for the final temperature. And from our ideal gas law, we will be solving for this one. The ratio of V2 over V1 to be 1/9. And from this, we can have the expression of T2 to be this one. Then just plug in values. We have the final pressure which is 21.7, and we know the initial pressure, which is just 1 atm. And we have the initial temperature as 27 degrees Celsius. That will give us 300, that's 273.15 plus 27, so we have 300.15 Kelvin. And from that, we solve for the final temperature, that is just 450.54 degree Celsius. So how hot is that 450.54 degrees Celsius? To give you some point of reference, our home flat iron on average has a maximum temperature of 250 degrees Celsius. So do not touch a running car engine. That is way hotter than your flat iron. And for our next example, we'll consider a mass of air inside a scuba diver's tank or a scuba tank. An empty tank used for scuba diving contains around 11 liters of air at 21 degrees Celsius. And because it is empty and open, it may have a pressure of 1 atm. When the tank is filled with hot air from a compressor, the temperature raises up to 42 degrees Celsius. And the pressure will considerably go higher, up to 2.11 times 10 to 7 Pascal. So what mass of air was added? Remember that air is a mixture of 78% nitrogen, 21% oxygen, 1% of unknown gas molecules with an average molar mass of 28.8 times 10 to the power of minus 3 kilogram per mole. So, first we will solve for the amount of gas. That is, we have these values. That's the initial amount of gas inside the tank. And once more gases are introduced and compressed into the tank, then we have this final number of gases. We have 88.5771 mole. So, the question here is, what mass of air was added? So, we need to take the difference between the final amount of gases and the initial amount of gases. So, we have the difference, that is N2 minus N1. And that will give us this value of gas. That's 88.1215 mole. Then, to determine the mass of the gas being added into the tank, then we simply solve for M. Remember, N is just the ratio of the mass of the substance and 1 mole of that substance. So, we simply use the given values. We have this number of gases and the molar mass of that gas, which is this one. Then we will have a value of the mass to be equal to 2.54 kilograms. In your free time, you might consider solving for the number of breath you can have for this amount of gas which is introduced into a scuba diving tank. So that's it for now. See you in our next lesson.